So we're now starting work on a new unit. This is Unit 8, equations of lines and planes. We're going to be looking at both R2 and R3. First lesson we're going to be focusing on will be R2, and we're going to be looking at vector and parametric equations of lines in R2. So we're going to start with a line that passes through the point 2, 4, and it has a direction vector of 5, 3. What would the line look like? If you have the notes in front of you, I would suggest that you follow along and try to do this on your own. First thing you should do is plot that point. So where's the point 2, 4? So there's the point 2, 4. What would the direction vector look like? It has its tail at the origin and it has its tip at 5, 3. So let's show what that looks like. And then every point on this line would need to follow that direction vector. So it's possible that I could shift 5 over from here and then up 3. It's possible I could shift 5 to the left and then I could go down 3. So let's show what that line looks like, and note it's following the pattern established by the direction vector in that these two are parallel. All right, let's move on to the next slide. So I now have a line that's passing through those 2 points, 1/4, -2/5, -4/8, 1/2. Find a direction vector for this line so that it has integer components. So remember, if you're going to find a direction vector, then what we're going to have to do is determine in terms of our vector whether we want it to be going this way, from here to here, or from there to there. If I want this to be the tail, then I'm going to imagine sliding that to the origin, and I will need to take away 1/4 from this, and I will need to add 2/5 to that. If I view this, I want to shift this to the origin, then I would add 4/8 and I would subtract 1/2. So you can make a decision as to which way you want to do it. In the end, we will get to the same direction vector. I have chosen to shift this being the tail, and I'm going to shift that tail to the origin to get my direction vector. So I'm going to subtract 1/4 from this, and then I'm going to take away -2/5, or alternately I'm going to add 2/5 to that. If we get ourselves a common denominator here, we will have 2/8 here. -4 minus 2 is -6/8, so that's going to give me -3/4. We're going to need tenths here, so this is going to be 5/10 plus 4/10. That gives me 9/10. So we have a direction vector, but the problem with the direction vector I have right here now is that it is not in integer form. That is to say, it doesn't have integer components. And we know any scalar multiple of this particular line will still be parallel to it. So what do I want to do? Well, the first thing I want to think about is if we think in terms of sort of a common denominator, right? A 3 could come out of those two. And so if I took a 3 out, I'd be left with a -1, and then I'd be left with a 3 there. But I would still have to deal with the denominator. So if we think in terms of a common denominator, the common denominator would be 20 here. So I'm going to try and take out 3/20. Now if I'm going to take out 3/20, so I'm sort of imagining factoring that out, then I would have to divide each of these by 3/20. And that's going to give me this. And again, how did we get that? I'm not sure how good you are with fractions. We would have to take -3/4 and we'd have to divide that by 3/20. Now dividing by 3/20 is the same thing as multiplying by 20/3. And now you can see the 3's would go, and then I'd be left with 5. So I'd also have to be taking 6, and then what I would need to do is multiply that by, not 6, sorry, that's not what we got there, we got 9/10. I need to take my 9/10, divide that by 3/20, which is the same thing as multiplying by 20/3. And then we see we're going to be left with a 2 up here, and I'm going to be left with 3 there, and that's how I get the 6. Alternately, you can expand to show that that's the case. So now that we've cleaned that up, we can now see that this piece here is my direction vector. Let me clear some of this out of the way now. I think I'll just delete that after I showed you how to do that. So now we can see this direction vector here has integer components. It is in simplest form, no fractions and no common denominators. And let's show what that direction vector would look like. And this is parallel to this right there. But this direction vector here, integer components, and we can see we can't get any simpler than that. On our next slide now, I'm going to give you an alternate way to think about how you could find the equation of a line. So point x naught, y naught is a given point on the line. So this is a point. I would have to give you this particular point. This is a point on the line. And then I'm going to give you a direction vector defined as a comma b. And then t times m, where t is any real number, is going to be a vector that's collinear with m. So notice right now there is direction vector m, and from here to there, that's a scalar multiple times direction vector m. So I am getting a vector that is parallel to this. Now look what happens here. We can take the vector that represents the point. The point vector has the tail at the origin and the tip at this point. And then what we can do is we can take the vector that has its tail at the origin but its tip at tm, and then I'm going to slide, so these vectors are together tail to tip, and then what I create is a sum. So I'm going to have green vector plus red vector is going to result in the sum that's the blue vector, and notice that that's a point on the line. Now watch what happens when I move my parameter t. See how when I move parameter t, I'm tracing out all points in the line. So this is a different way to think of the equation of a line. You're normally used to maybe y equals mx plus b. I give you an m, I give you a b, and then you use x. X will then drive y, and you'll create points on the line. So in this particular case, what's happening when we create a vector form, I'll show you parametric later. When we create a vector equation of a line, what we have is two vectors we're going to add together. We're going to add together the green point vector. I'm just going to select the green part, and then we're going to add to that all scalar multiples of the direction vector. So notice how Tm, which is a scalar multiple times our direction vector m, notice how that length changes depending upon what m is. If I allow t to be 0, then we are exactly the direction vector. If I allow t to be 1, I am the direction vector. If I allow, or the direction vector units away, I will say, from my point. If I allow t to be 0, notice I'm right on the point. And then when I allow t to be negative, I'm tracing out points to the left of the line. So again, recapping. If t is negative, I'm tracing out points to the left of the given point. And when t is 0, I am on the given point. And when t is positive, I'm tracing out points to the right of the line. Now, having said that, if we can understand how this picture is created, green vector plus red vector, which is all scalar multiples of the direction vector, gives me blue vector, and the tip of that blue vector is tracing out a point in the line. So this point here, that vector is going to trace out all possible points in the line. So that will give us some new ways to think of the equation of a line. So the vector equation of the line now, maybe I should have thought of that in blue because that's really tracing out points in the line. But vector r is equal to r naught, which is my point vector, plus t times my direction vector. In component form, this has coordinates x naught, y naught, plus t times the tip of the direction vector as at a comma b. And then if we do expanded form, the x component would be x naught plus t times a, and the y component would be y naught plus t times b. And now to switch that to what we would call parametric equations, we would now write that the x coordinate of this line is equal to x naught plus t times a, and y is equal to y naught plus t times b. So what I'm going to do now is I'm just going to jump to Desmos just to show you, because this is a different way of thinking about graphing a line. So you're typically used to seeing, this line. For this line to be graphed, I'd need to know its slope, and I would need to know its y-intercept, and then I would plug in an x, and the line would be traced out. Well, I'm now defining this parametrically as x naught which is the point on the line, which is 1, comma 1. So x naught plus t times a. And in my direction vector, my a, let's close that for a sec. And my direction vector, my a is -2, and my b is 1. So my direction vector is -2, comma 1. And that would give a slope of -1/2 for my line. And the point 1, 1 would be on the line. But what we do now is notice when I change parameter t, see how it's tracing out all the points on the line? So this is called a parametric equation. And in a parametric equation, you have equations for your x-coordinate and your y-coordinate in terms of a third parameter, and in this case that parameter is going to be t. So that's how we're going to create the equation of the line. All right, back to GSP now. So we're going to jump over here. In vector and parametric equations of lines in R2. So our vector equation is going to look like this. R naught, so again, this is a point on the line. It has a vector, tail at the origin, tip at the point on the line, plus t, where t is a parameter, times our direction vector m, which has its tail at the origin and its tip at the point a, comma b. We can write it in component form as xy equals x naught y naught plus t times a, comma b. Again, t is any real number. This will be important to write this down. We have to allow t to assume the values of all real numbers in order to trace out the entire line. Parametrically, the x equation would be x naught plus ta. The y equation would be y naught plus tb. T is any real number, and I've already mentioned where that came from. And then I showed you in here how we change t, and it's tracing out points on the line. And this is illustrating how vectors come into play. And then I also showed you in Desmos, these are considered parametric equations. The line is being defined in terms of the parameter t, and I have to allow t to be all real numbers if I want to trace out that whole entire line. All right, let's move on. So if we're thinking about horizontal and vertical lines, so for a horizontal and or a vertical line, what needs to happen? So we're going to have to think about what the direction vector needs to be. We're still going to need a point on the line. So in this case, the point on the line is 2, 0. But if you want a line to be horizontal, what needs to happen? So I need it to be parallel to the x-axis. So I'm going to need the direction vector to be parallel to the x-axis. And of course, the direction vector for the x-axis is 1, 0. And for a vertical line, I need to be parallel to the y-axis. So what I'm going to need to happen is I'm going to need my direction vector to be 0, 1, or the y-axis direction vector. So the equation of a vertical line will be x naught y naught plus t. I guess I really could write this as vector j. And for a horizontal line, we could be x naught y naught plus t times vector I. All right, so continuing. What about parallel lines? What would happen for parallel lines? So parallel lines would not have to have the exact same direction vector. What I'm noting is that they must be scalar multiples of some direction vector. So I'm writing here T1 times AB, T2 times AB, where T1 and T2 are scalars in the real number set. So if these lines are parallel, they must be scalar multiples of some kind of direction vector. So let's see. So for this particular direction vector here, let's say the green one, we could say 2, 3, right? So in describing our traveling, 2 over, 3 up, so 2 to the right, 3 up. But for this particular line, the direction vector could be -4, -6. So these aren't the same direction vector, but they are scalar multiples of each other. So we now could rewrite this one as -2 times 2, 3. So as long as you can show that the direction vectors for two lines are scalar multiples of each other, then those lines will most certainly be parallel. All right, what we're going to do next is we're going to think about perpendicular lines. How could you tell if two lines were perpendicular? We know how to do that in grade 9 math, we learned that if we're talking about slope y-intercept form, the slopes would need to be negative reciprocals. So how would that play out in vector forms? So what would have to happen if we're going to think about this is if they are perpendicular. So let's think about, I have a direction vector AB. If the two lines, let's dot this with, put an extra bracket there, so let's ignore one of those. Let's ignore that one. If I dot that with the direction vector for the next line, which maybe I will call m comma n, then what needs to happen is a times m plus b times n needs to be 0. Then they'd be perpendicular. An alternate way to think about this, because we are in R2, is to think about, we have a slope of 2. Let's say we have a slope of 2/3. Then the slope of a line perpendicular to that would be -3/2. As a direction vector, though, we start with the y component or the x component first. That would be 3, 2. So that's perpendicular. This is vector form. So let's put a vector over that. Ignore that. And then the perpendicular one would be written as 2, -3. So then if we want to think about generalizing, so let's say the slope of my line is a over b. The slope of a line perpendicular to that would be -b over a. And so then what would happen is, in component form, my direction vector would be it would be b comma a, because we have to start with x first. And then the direction vector, something perpendicular to it, would be -a comma b, or we could write a -b. So generalizing, what we're noticing is that the components switch place. That's not surprising, because when we do a reciprocal, we turn it upside down. So the x component has become the y component, so they should switch places. And then we also need to account for a sign change. So notice if both of these are positive or both of these are negative, then one of the components here would be negative. So coming over here, if I have a line, R1, then two possibilities for lines to be perpendicular to it. So the direction vector here is a comma b. Notice how the components have switched places. It's b comma a, and now we need one negative. So -b comma a or b comma -a. And I'm noting I gave the same scalar to this one. Again, they do not have to be exactly the same. They just need to be scalar multiples. So any scalar multiple of AB, then this one is any scalar multiple of -b over a, or -b comma a, or b comma -a. So, and then in this example here, I'm showing you if the direction vector is 3, 2, then the direction vector of something perpendicular to it would be 2, -3, or -2, 3. And then you can check with the dot product just to make sure. So dot product wise, we would get -AB plus AB, which is 0. We would get AB plus -AB, which is also 0. All right, moving forward. Find the vector and parametric equations of a line that passes through the point 2, 5. It has direction vector -2, 2. Draw the line and find 2 points on the line. And then we would need to also think about are the points 20, -13, and -30, 36 on the line. Lots to unpack in this question. Okay, so the first thing we need to think about is what was the vector equation? And we'll take you back to, I think that was on slide 4. Let's go back to slide 4. Slide 4, so vector equation. So we need the point vector plus a parameter times our direction vector. So coming back over here, we need our point vector, so we can get our point vector from here. Tail 0, 0, tip here, there's our direction vector. So the vector equation of our line is going to look like this. R equals, don't forget to put R equals, and again, the symbol for a vector is like that, but there is no such symbol in Geometry Sketchpad. So what I'm doing right now is I'm just using the symbol for array to work my way around this. So there's the point vector 2, 5 plus t times the direction vector -2, 2, where t is any real number. So we've done the vector. Now for the parametric equation. So if we think about the parametric equation, there will be two of them. There will be one for the x component and there will be one for the y component. The x component should be 2 plus -2 times t. So 2 plus -2 times t. The y component should be 5 plus 2 times t. So there are our parametric equations. And then what's next? Well, I suppose we should give some thought to, because I'm just noting this now, that direction vector is not in simplified form. We could simplify this direction vector down to -1, 1, or 1, -1. So what I'm going to do here is show you a simplified version. So if we use -1, 1 as a direction vector, then we're going to change this to 2 minus t and y equals 5 plus t. So now how do we find points on the line? You are used to choosing an x and then plug into the slope y-intercept form of the line to find the y-coordinate. That's not how we do this here. As I showed you in, maybe we'll just jump back there quickly, as I showed you when we have parametric equations, we choose a t. And that t will then determine what the x and y coordinates are. So if we want to find 2 points on the line, we're going to pick a random t. So what t am I going to choose? I'm going to choose t of 6. It doesn't matter what you choose for t. Actually, I should rephrase that. It doesn't matter what you choose for t. You cannot let t be 0. If you let t be 0, can you imagine plugging that in here? What are you going to get back? You're going to get the point 2, 5 back. That's not another point on the line. You can pick a t that's easy to work with if you want a t that's easy to work with, and maybe 1 or -1. Now what I'm going to do is I'm going to plug 6 in for t, I'm going to plug 6 in for t. And that's going to give me my x-coordinate, 2 minus 6 is -4. My y-coordinate, 5 plus 6, which is 11. So now that gives us the point -4, 11 is on the line. For a second point, choose a different t. I'm going to choose a t that's negative now. I'm going to let t be -4. And again, I'm going to plug in here 2, take away -4, 5 plus -4. So that gives me 6 for my x component or x coordinate and 1 for my y coordinate. So therefore the point 6, 1 is on the line. All right, so now we've done vector parametric, find, oh, I didn't draw the line, so I guess we should draw the line. So the point 2, 5 is on the line, so let's show that. The direction vector is -2, 2, so let's draw that. There's that direction vector, which is really -1, 1. So that simply means that following that direction vector, there'd be a point here, 1 there. Following it in the other direction, a point there, 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 and there. So the line is going to look like that. All right, now we have to answer these questions. Are the point 20 and -13 on the line? Are the points -30, 36 on the line? So let's think about this first one. So how are we going to know if a point's on the line? What we're going to do is we're going to check there is a certain t value, let me put it that way, that will return an x coordinate of 2. So I'm going to try and find what that t value is. I'm just going to plug a 20 in here, and then I'm going to isolate that for t. So 20 equals 2 minus 2t. I actually went all the way up to that one up there. Doesn't matter, I could have used this one, but since I chose to use this one up here, I'm then going to have to check my y for that one. So 20 minus 2t, that gives me -2t. 20 minus 2 is 18, and that gives me t is -9. So what I'm going to do next is I'm then going to now check. I now know if I plug a -9 in here, I get 20. So I'm going to plug a -9 in here, and I'm going to ensure that I get back a -13. Or alternately, I'm going to plug negative 13 in here, and I'm going to isolate that for t and make sure I get the same t back. So in my case, I've just chosen to plug in the negative 9, and I'm going to see what happens. 5 plus 2 times negative 9 is indeed negative 13. So this point is on the line. How do I know that? Because when t is negative 9, it returns negative 13, but it also returns 20. Again, plug a negative 9 in there, you get 20. Plug a negative 9 in there, you get 13. So that point definitely on the line. All right, so for the next one, you're going to do it the same way. Starting here, maybe plug in the negative 30, or you can plug in the 36 here. Find what t value you get, and then show that t value when plugged into the other parametric equation gives us the point we're after. So I'm going to do it the same way I did before. So I'm going to start by plugging in negative 30 here. Negative 30 equals 2 minus 2t. Negative 32 equals negative 2t. T is 16. And then I'm going to plug the 16 in for the parameter t up here, and I'm going to see what happens. So, well, actually, I didn't do that. So now I'm showing you an alternate way to do that. I'm plugging the 36 in here, equals 5 plus 2t. So 36 minus 5 is 31. It's 2t. That gives me t is 15.5. Notice those are two different t values. We need a t of 15.5 to get the 36. We need a t of 16 to get the negative 30. Therefore, the point isn't on the line. Now, let's see if I have some space to write so I can show you in this particular case what would happen if t is 16. Then we would get y is equal to 5 plus 16 times 2 is 32. So y is 37. So we have the point negative 30, comma 37 is on the line. And now what would happen with 15.5? So let's plug that into here. 2 minus 15.5 times 2 would be 31. And 2 minus 31 is negative 29. And now that means the point negative 29, comma 36 is on the line. All right, so we've addressed all of the possible answers there. I've shown you several different ways to approach determining if a point is on the line. Any way you do it, you do have to find what t will work for one of the coordinates and then prove that that same t works for the other one, or show that it happens to be a different t. All right, next example. Find the vector and parametric equations of the line that passes through negative 2, 4 and 3, 5. What are the coordinates of the points where the line crosses the y-axis? So the first thing we need is a vector equation. And what do we need to find a vector equation? So summarizing what we need. What we need is a point. I'm going to write it that way, and then I'm going to write D like that with direction vector. So we need a point and a direction vector. We actually have 2 points. So we're set for the point. What we don't have right now is a direction vector. Can we find a direction vector? Certainly we can. We can use these 2 points to find a direction vector. I can either imagine sliding this back to the origin, taking away 3 from that point, taking away 5 from that point, or alternately I can imagine sliding this to the origin and making this the tail and this one the tip, and then I would be adding 2, and then I'd be subtracting 4. Alternately, I can view this as a journey to go from there to there. I can see that's plus 5, and to go from there to there, I can see that's plus 1. However you want to do it, but we do need the direction vectors. So if this is at the origin, and I leave that as my tip, then when I find the form through the origin, I'll get 5, 1. If I do it the other way, and I view this as the tail and this one as the tip, then it's negative 5, 1. Now remember our vector equation of the line. How does it work? R is equal to vector for my point plus t times my direction vector for my line. And then I have to note that t is any real number. So let's see what that's going to look like. So I have two possibilities for points, right? I could choose -2, 4, which I've used, or I could also use 3, 5 here. So I do have choices here. Plus 5, 1, and I've noted that t is any real number. On a test, I would not want you to use this because this has two negatives, and in math we always try to minimize the number of negatives. But let's suppose the direction vector for the line was -1, 2. Which we could also write as 1, -2. Either of these would be appropriate to use. In this case, you shouldn't be using this one. Now, because as I mentioned, too many negatives. Minimize the number of negatives. Now, what's the parametric equation? So the x component, or my equation for x, would be -2 plus 5t. My y component, or my parametric equation for y, would be 4 plus t. So there are parametric equations, and I'm just going to show my note on the bottom. We could use any combination of both points and direction vectors now. Direction vector 10, 2, that would also work because that's a scalar multiple of that. But let's say this is what we will agree to. Simplest form. I want the direction vector in simplest form, and what does that mean? No common factors that could come out, and we've reduced the number of negatives. I'm going to repeat that one more time. I want your direction vector to be in simplest form, which means minimizing the number of negatives and having no common factors. All right, so now what's the next part of this question we need to address? What are the coordinates of the point where the line crosses the y-axis? So what's true when you cross the y-axis? What do you know about the y-axis? Certainly on the y-axis, the y-coordinate is changing. What isn't changing is the x-coordinate. The x-coordinate is stuck at 0. So on the y-axis, x is 0. So what I'm going to do now is I want to try and find the t value that would give me an x of 0. So I'm going to plug a 0 in here. 0 equals -2 plus 5t. And then what I'm going to do is isolate for t. So I'm going to get 2 is equal to 5t. T is equal to 2/5. So I now know that t is 2/5. So what I need now is the y-coordinate. So what I will now do next is I will plug in the 2/5 into here. I pointed there, but that's the wrong equation. It's this one is the parametric equation for the y component. I'm going to plug 2/5 into there. So y is 4 plus 2/5. If I get a common denominator, I'm going to get 20/5 plus 2/5 is 22/5. And so now my y-intercept is going to be 0, 22/5. All right, that brings us to the end of this particular lesson. We were looking at an alternate way. I guess we'll jump back to slide 4. So slide 4, a different way to write the equation of a line. I know you're used to slope y-intercept, but we can also define the equations of lines in R2 using vectors and parametric equations as such. So we need a point, we need a direction vector. Parametrically, we can write the x component in terms of the x component of the point on the line plus t times, that's the x component of the direction vector, the y component of the point, the y component of the direction vector. And then we went through and covered, you understand that if lines are horizontal, their slope is 0. But if lines are horizontal and we're dealing with a vector equation, then we need the x-axis vector, which is 1, 0. Now, when lines were vertical, we learned that you couldn't write them as y equals mx plus b. We had to write them as x equals something. In vector form, we simply just need our direction vector to be the j vector or the y-axis vector. And then we learned that if lines are parallel, then we're not going to check to see that they have the same slope. What we're going to do is see if we can write their direction vectors as scalar multiples of each other. Then they'll be parallel. With regard to perpendicular lines, I'm just going to delete that. We know that from grade 9 math, their slopes would need to be negative reciprocals. In calculus and vectors, we're going to learn, of course, that the dot product should be 0, or alternately, if the direction vector of the line is AB, then the direction vector of a line perpendicular to it will have the coordinates swapped. So instead of AB, it will be BA. And then really, I'm going to word it this way, you need to switch the sign of only one of those components. Don't switch the signs of both, just switch the signs of one component. So if you've made it to the end of this lesson, once again, thank you for watching. Stay tuned for lesson 2, and as always, stay safe.